Hey guys, happy snow day. I'd like to do a quick video lesson filling in the gaps for what we're missing here in class to try to get us to a point where we can solve some WebAssign problems. If you recall, what we've been talking about up to this point was electric field strength, and we use the analogy or the comparison to gravity to help understand this concept. And so if you're looking at gravity, if I had the Earth and it has mass, and I had the moon, each of these objects have their own gravitational field that attract anything near them. However, you can have multiple fields interacting, such that if I put some object in the middle, that object is going to feel an acceleration due to gravity from the Earth, and it's going to feel a smaller acceleration due to gravity from the moon. And if you recall our equation, the acceleration due to gravity coming from Newton's law of universal gravitation was big G, the mass of the object causing the gravitational field, over the distance to that object squared. And so if this is the distance to Earth, then the distance to the moon would be that distance. Those are the values that go in the denominator to solve the problem. Now, so if I was an object sitting in the middle, I'd want to know what my actual acceleration is, and that's where we get a total gravitational field. AG total would just be the vector sum of the acceleration due to gravity on Earth plus the acceleration due to gravity from the moon. And these be two numbers that I can just plug in my big G equation. G, mass of the Earth, over the distance to Earth squared, plus big G, mass of the moon, over the distance to the moon squared. These are going to be two numerical values that are both accelerations. Now, what's tricky, though, is if I plugged in numbers, both of those values are going to be positive values because mass is always positive, distance is positive, G is positive. However, it's clear if you look at your picture that adding them as vectors, that one of them is to the left. And so assuming Earth is pulling more, you're going to have a total field to the left. So it's important that we assign a direction to these values. So I would say that this one becomes negative, and this one becomes positive. And that's determined from our picture. Sorry, I'll make that a negative sign. And so whatever numbers I get when I plug into those values, I attribute a negative to it, and the other one a positive. Again, it's from my picture. They both are attracting, and they're going to be canceling each other to some degree. And I'm going to get a total field, most likely at this position, towards the Earth. So any object placed there will accelerate towards the Earth. So this is the same premise that we deal with electric fields. So in this case, if I have field A, which has a negative charge, and field B, which has also a negative charge. We'll just keep them negative. And again, I'm using negative because that would attract a test charge, and that's very similar to gravity. Then any charge placed in the middle, call it a test charge, positive Q, would feel a field from A, and we'll assume A is larger. There's the field of A, and a field from B, and the total field, E total, would again just be the sum of A plus the field of B. And we have a field strength equation, recall. The field strength is just big K, another constant, times the charge of the source over the distance to the source squared. So again, if I designate this is the distance to A, and this is the distance to B, then when I plug in, I'm going to have K, the charge of A over the distance to A squared, plus K, the charge of B over the distance to B squared. And just like what we talked about with gravity, but we're going to plug in values. Now in this case, both charges are negative. So you might assume that you would get a negative plus a negative to get a negative field. However, if you look at your picture again, one of those arrows points to the right. So we have to be really careful when we just plug in numbers for the charge and in the negative sign. All the negative means is that it will attract a positive test charge. So from my picture, as I've drawn it, the field from A will end up pointing to the left. So whatever number I get here, I'm going to call it a negative value. And whatever number I get from B, I'm going to call it a positive value. And if A is larger as a source, it'll likely pull more to the left than B would pull to the right. And so I might get a negative answer, which would indicate only that the field points to the left. So these are the premises that we've been doing up to this point to calculate field strength. Now, where I want to go from here is actually figure out what forces these objects will actually feel. And this is where we have to go back to what we've done with gravity before. So if I create a little bit of space here, and I have a gravitational field in between the Earth and the Moon, well, that object is going to accelerate. And if I wanted to find the force on that object, or any object, if you recall, Newton's second law says that F equals ma. And so the force of gravity is just equal to the mass times the acceleration due to gravity. Right, this is something we've done before, and this is also, again, known as weight. And weight just depends on how much mass we put in that field. If I put a proton in there, there wouldn't be a big force. If I put a large car, that mass in the right side just gets bigger. The field hasn't changed. The field is the same regardless of the object we put in it. All right, and if we all stand on scales, we would all weigh different things, even though we're in the same field at the surface of the Earth. Now, this equation actually leads us to something we've already learned, which is that Fg equals, again, Ag is big G, the mass of the object, over the distance to that object squared. And if we multiply it by the mass that's in the field, we get our equation. And this one should look familiar to you. This equation was Newton's law of universal gravitation. All it is the field strength due to gravity, this part, times the mass that's in the field. And so if we look at our analogy between gravity and field strength due to an electric field, you might assume you get something similar, right? If acceleration due to gravity is similar to electric field strength, then the electrostatic force should also equal not mass times acceleration, but looking at mass and charge. Sorry, I'm back. My computer crashed on me here. As we were just saying, we have Newton's law of universal gravitation, which we've already learned. And as we talked about the analogy between gravity and the electric field, right, we could say that Ag is similar to field strength, and mass is similar to charge, such that if the force of gravity equals mass times the acceleration due to gravity, well, then it would be safe to assume that the force due to an electric field is not mass, but charge, and not acceleration due to gravity, but field strength. And this is an equation that we're going to use now, such that if I know the field strength, all I have to do to figure out the force on a charge brought into it is multiply that field times the charge I bring into it. And this actually, similarly to how we got our Newton's law of universal gravitation, I can plug this in to get an equation that says field strength, K, times the charge of the source over the distance to the source squared, times the charge that's brought into it, a second Q, right, gives us our force. And this equation here is what we call not Newton's law, but Coulomb's law. In the past, I've taught you this first, and we've worked backward to field strength, but I'm hoping that this makes a little bit more sense. Again, this right here, this part in here, is just the field strength that we've already calculated, and now I'm just multiplying by the charge we brought into the field, just like we would multiply the acceleration due to gravity times the mass we brought into the field. Another way to think of this equation is just to look at the units of field strength. Right? If you recall, field strength has units of newtons per coulomb, which is really just force per charge. And so you can look at this equation and it leads you right there again. If I multiply both sides by charge, I get force equals charge times field strength. So let me real quick give you one quick example, all right, where we actually calculate the force on an object. So as we've done before, if I have a source, call this A, and it has a charge of negative 40 microcoulombs, and I have a second object, we'll call this a test charge, call this B, and it has a charge of positive 20 microcoulombs, and I want to know what is the force on B. And I'll tell you that there's a distance between them. We'll call it 10 centimeters in between. I think that's enough information to solve it. And as we've done before, we found the field strength at B. The field at B would just be Kc, the charge of the source, which in this case is A, over the distance to A squared. And we can find a value for that. That's 9 times 10 to the 9th. It's K. The charge of A is 40 times 10 to the negative 6. That's where we get the micro. Now, again, I left the negative out because if you look at your picture, A should attract B. There's the field of A, all right, which is to the left. But if A was positive, it would repel B. So I'm just going to leave it out. We'll let my picture handle that. And the distance between them is 10 centimeters or 0.1 centimeters squared. So I can get my field strength from this equation here. I'm going to open up my calculator and clear it out. I've stored K. Alpha K I've already stored in there, the store button. So alpha K times 40 second double e to the negative 6. That's my numerator, divided by 0.1 squared. And I get a value of, how many zeros is that? It looks like 36 million. 3.6 times 10 to the 7 newtons per coulomb is the field strength. And at this point, it's to the left or towards A. And again, it would be a negative if I plugged in. It only tells you it's attracted to A, which is why it's to the left. If I want to find the force on B, well, that's just the charge of B times the field strength at B, or from A. We'll call that A, which is just the 20 microcoulombs, 20 times 10 to the negative 6 times the field strength. And I'll put in my units here. This would be in coulombs times 3.6 times 10 to the 7 newtons per coulomb. And again, as you see, the coulombs cancel and we get left with newtons. And I'm going to take the answer and multiply by 20 second e to the negative 6. And I get a value of 720 newtons. And the direction of the force would be in the same direction of the field. So that would be towards A. And I could have gotten this by plugging right into our other equation. I can take my Coulomb's law equation, which is just K Q1 Q2 over the distance between them squared. I would get 9 times 10 to the 9th. The